Hi and welcome to the Elements of FAIR video series. This tutorial focuses on interoperability of data. Interoperability means that data can be exchanged or combined with other data. It should be possible to move data between services and systems without the information content being disordered or lost. Data and metadata should be unambiguous so that all users, both human and machine, can interpret it correctly. It is responsible research to take interoperability into account, and there are many benefits from it. The quality of the data will be better, the data or metadata is machine actionable, the data won't be misinterpreted nor misused by mistake, you can combine data to other datasets yourself too, and interoperable metadata increases the visibility of data. Interoperability can be divided into 4 levels. Legal interoperability includes, for instance, well-aligned licensing and data protection regulations. This ensures that data publishers and users understand the legal framework and policies in the same way. Organizational interoperability ensures that processes and governance work well across organizational borders. Technical interoperability is about technical implementation, and it creates the basis for semantic interoperability, where information systems can operate seamlessly. Semantic interoperability highlights that metadata and data should be understandable both for humans and machines. This means you should use controlled and machine-readable vocabularies to describe data. There are 3 main things to remember when considering how a machine understands versus how a human understands something. Let's take, for example, a table with numbers. Without information what the numbers in a column are, it's impossible to interpret the data. We also need additional information about the variables. For example, if we have measurements such as weight or height, we need to know if the variables is in kilograms, grams, pounds, meters, feet, or something else. Also, blank values are very difficult for machines. It is important to tell the machine what the zero value is so it can be distinguished from a missing value. The meaning of a word can differ depending on the context. A human understands, for example, when talking about green plants, that this refers most likely to trees and flowers, but a machine can interpret this also as power plants. We need to distinguish between the content or meaning, usually called concept, which represents the content on an abstract level, and the term, which is a string of letters which a human user understands. Take for instance this little white wood anemone. In Finnish it's called valkovuokko. The scientific name is Anemone nemorosa, and in Swedish it's called viitsippa. The concept also has a globally unique persistent name. This can be told to the machine in a way it can easily process. Furthermore, we might want the computer to know that the whitewood anemone is part of the anemone genus. This way, by separating the term from the concept, we can help machines process meaning. We can code this in dedicated datasets called semantic artifacts. Semantic artifacts are machine-actionable models, such as controlled vocabularies or ontologies, which make terms understandable also for machines. For example, when a computer understands the concept of the whitewood anemone, it understands searches also with synonyms such as valkovuokko in Finnish. In the simplest way, this is done by defining a list of words, strings, that the machine can retrieve. Because the semantics is low, you can only get match when the letters in the word are exactly the same. For example, when searching for United States from a list of countries, you cannot get a match if it's listed as USA. A degree more complex semantic model is a hierarchy, where terms can be grouped into upper and lower concepts. However, neither the list nor the hierarchy define other relationships between the concepts. In our example hierarchy, the wood anemone belongs to the upper level of wild plants. Strong semantic interoperability arises when relationships between concepts can be modeled rather than listing individual terms. For example, a thesaurus may contain not only a term and its synonyms or language versions, but also a definition of the meaning. The strongest semantics is reached when ontologies are used. An ontology model gives meaning to the relationships between concepts, and it can also define partial overlap between the concepts. Using controlled vocabularies and ontologies has many benefits. They enable intelligent searches and predictive text input, which are utilized also on the commercial side. In many online stores, you might have, for example, seen sections where the store tells you, people looking at this item were also interested in this, or the site recommends you similar products. But where to find vocabularies and ontologies for science? In Finland, the most well-known service is Finto, which is a centralized service for interoperable thesauri, ontologies and classification schemes for different subject areas. You can use Finto to browse vocabularies or integrate the vocabularies into your own systems. Research fields and disciplines have their own vocabularies. For example, life science ontologies can be found at Bioportal. It requires a lot of know-how both from researchers and data stewards to choose a vocabulary that works with the data. You can use lookup services such as the linked open vocabularies or Bartok to find suitable terms and vocabularies for your needs. Additionally, you can find data repositories supporting your preferred controlled vocabulary in registries such as FAIR-sharing or ReadData. Above all, good data management planning and the utilization of common standards, practices and solutions can promote data interoperability. When interoperability has been taken into consideration, it is possible to combine data from different sources automatically, without retrieving independent information about the data case by case. Thank you for watching.